Viva la nebula. As I paraphrase something Chuck likes to close his emails with. My name is Ron here, and I'm in here for Jerry Wilson, whose picture, his face may appear on the screen. You never know, he's in Dublin, Ireland, which is, what, 1:30 in the morning? Maybe 2:30. But as the VP, I'm a heartbeat away guy, and I thank you all for coming. Welcome to our Friday night, August the 2nd, big party, another LCO event. The last one we had featured a young man from Las Cumbres Observatories out in Toledo based for the Worldwide Telescope Network, who was involved, if you recall, you were there, with photographing using radio telescopes, I think, the interior of the galaxy, the Sagittarius A black hole. That's what Joseph Farah talked about. And that night we overflowed Farron Hall, if you remember. Never forget. Glad the fire department wasn't here that night. Tonight is Fiesta downtown. That's where a lot of people are. Very little traffic coming here. Did you notice that? Yeah. Tonight, we got my good friend brought me a guy I watched do a talk in the back patio area of that downtown tavern called M Special. It's technically a restaurant, so you can bring kids and you can be in there under 21, and so all those young people from City College come, and university people. It's a little younger crowd, but it's okay. We're going to get them in here at some point. And I was there on March, whatever the second Thursday is, they do what's called Astronomy on Tap. And our esteemed guest speaker did an interesting half hour. And it's a little longer tonight, so it may just fill up a whole hour or less, depending on our questions. And I'm going to treat it like a big, long, well, not a joke, obviously, but there's a punchline, let's just say. Ethanol in the ether. What could that possibly be? Tom was running toward me, so what the heck is going on? Am I not being heard?
No, you're fine. It's just I'm going to click something on your screen.
Oh, by all means. I want to pay tribute to some people who are here before we get to our regular meeting stuff, and we'll bring Nikolaus Volgenau on in about 5 or 10 minutes. But first of all, let's do my regular instant poll. I'd like to know how many people here for the first time ever at one of our meetings. Raise your hand. Just all right. How many of you, I was expecting a bigger crowd, but Viva la, you know what? How many of you are LCO followers? You go to all their events. All right. Very good. Now, members of Santa Barbara Astronomical Unit, raise your hands. There you go. That's the home team that's going to take the rest of everybody out to beer and wrestle. How many people here teach astronomy up at Santa Barbara City College? Why aren't you in Dublin with Jerry showing him the sights? I'm not sure that's where you're from, but God love, I tell you. I was out there 25 years ago, and I was the token old guy inside the forums that would ask all the stupid, silly questions. And some of the quiet, shy ones would tell me on break, hey, you were asking, so that's what I was thinking. So I now do that on a regular basis, because I'm not the expert here at all, but I'm with some of the most intelligent people in the world, if not just Santa Barbara, that I work with. Old research and development engineers and scientists from out in that area of Hollister and Toledo, where LCO is located now. And we do a Monday morning vlog. Jerry likes to call it a podcast, but that's hearing only. You can see us on YouTube. If you can remember, SBAU Astro Hour. We're into our 4th year. We're almost halfway through. And it's Monday mornings, 11 to noon. Next Saturday night, we will have, starting in the afternoon, if you're a member, or you want to come on board, we have our 4:30 planning meeting on Zoom, Saturday afternoon of next Saturday. That should
tomorrow.
Be, no, it's not, is it tomorrow?
Yeah.
No, second Saturday.
I'm about to call you up, you'll explain for that. Anyway, we do it, yeah, the start party is the second Saturday. We're out at Camino Real. When are we at Camino Real, Chuck?
Tuesday the 13th, second Tuesday of the month.
Second Tuesday, Camino Real. We're in a brightly lit shopping center, setting up telescopes. And we're going to Westmont the third Friday, right?
Friday.
At dark. And now that we're in August, we're getting incredible night skies. So plan on joining us. As far as I'm concerned, we are the fun club of not only the museum, but of the whole town. We like to have fun. We're getting a little old in the tooth, some of us. The last really young person, I replaced him. He went down to Caltech, got a scholarship, cheap excuse, but we lost him. He was a 17-year-old disgruntled student who was my predecessor as vice president. And Adrian has now, I believe, changed his major from astronomy to mathematics. I believe he went across the street. Anyway, we got a great show for you tonight, but first of all, let's find out what's going on in town with our club. And here she comes to sell us some merchandise, our lovely merchandise manager, Pat McPartland. And she's got the new calendars in. One of those I've already paid for, so don't come up and grab them all. Or I can wait and get it.
Okay. Is it going there? Yeah. Okay. Seems no. Okay. All right. See, I'll take this. Okay. All right. I guess I'm going to hold this. My name is Captain Partland, and I'm not only the treasurer this year, but also I'm the merchandise manager. And so this is kind of my commercial time. We have all kinds of shirts and hats and tote bags. I brought up a tote bag with me tonight. Really nice. They have little holders here for your Kleenex. If you're like me, I'm devastated by allergies, so I put my little Kleenex packs in here. They also have a zippered compartment inside, and they're only $25. We just sold the last blanket tonight, so those are now off the shelf, you might say. And then the new that I have, is I have the 19, or not 19, you can see what my rating is, the 2025 calendar from Astronomy Magazine. This one I broke open so you can take a look inside, and it's really cool. And the best thing about these, they don't need a battery. So you can give them as gifts to friends for Christmas. Christmas is coming, so makes a good gift. They're down here in the box. You just pay me and then come and get your calendar. They're only $10. So definitely think about a calendar, or 2, or 3. What else? You can reach me on mgr@sbau.org if you have any questions. And we will work something out if you're interested in any of the items here. In September, at the September meeting, I'm going to bring all these items, the clothing, the tote bags, the mugs, the hats, so that everybody can see what we've got. And hopefully, we will clean out the inventory a little bit. So thank you for your time, and I will turn you back to Ron.
Is that mine?
No.
Oh. Why don't you just leave mine in my seat, and then, along with that other gift we have from Mr. Nicholas, will hold my chair. Thank you, Pat. As far as I'm concerned, give her a big round of applause. And as far as I'm concerned, nobody asked me, but I don't care. I'm going to tell it right now. The people that have been in this club and do the most, the heart and soul of SBAU is Chuck and Pat McPartland. Chuck, it's time for our outreach. Look out, you got a taste of it. You'll repeat some of that stuff. And the man's awesome. And I'll tell you who's coming. Oh, we'll have also our rumpus room lady. Go ahead.
Okay, thanks, Ron. Yeah, as you noticed when I spoke up back there, I have a bad habit of correcting Ron on everything, even when he's right. Okay, so we have a busy set of weekends for August for outreach. We don't have schools during the summer, but the campgrounds make up for it. So tomorrow night we're at Kachuma, set up at 8 p.m. We have a slideshow in the Fireside Theater, and then telescopes set up in Dakota Plains for the campers. And then and the public is welcome, but they charge you $10 a carload to come in if you want to come up for that. The skies are usually pretty good. Check the weather before you drive up there, though. And there are some mountain fire cams that you can check, fire webcams, to get an idea of what the weather's like. And then the National Weather Service has a satellite feed that has an animation loop, and you can get an idea of whether it's going to work or not. And because we're back in that weird weather cycle here where it's iffy. Then on Friday, the 9th, we have Refugio State Beach. Refugio just reopened. They were closed, and we were doing our outreaches at Carpinteria State Beach instead, but Refugio has a nice, much better venue in that it's closer to all the campers, so we get more people coming by. And then on Saturday the 10th, second Saturday of every month, the Santa Barbara Museum of Natural History right here, we have a public star party over by the observatory. And that will be starting at 8:30. Most of these other things are starting at 8 p.m. Then on Tuesday the 13th, second Tuesday of every month, it's Telescope Tuesday out at the big box. And like Ron said, there's a lot of lights there, but we try to make sure we have the most possible first quarter moons of the year. So that's why it's second Tuesday of the month, and it may wander from year to year. Then Thursday the 15th, Carpinteria State Beach with telescopes. And then on Friday, third Friday of every month, it's Westmont Public Telescope Night. Then Saturday the 17th, Kachuma Lake again. They're hitting us hard. But we get free campsite to make up for that for our annual camp out. Then on Friday the 23rd, Refugio State Beach again. Then Saturday the 24th, Kachuma again. Then on the 30th, we have Los Flores Ranch Park up in Santa Maria with a star party. And that's a big park up there that's a former oil drilling area. And 6245 Dominion Road is their main entrance. But we go a little bit farther along Dominion Road towards Santa Maria, and there's a dirt road, and there should be a sign saying turn in here. And that goes up to a nice little dark area where we set up telescopes. And then rounding out the month on the 31st, we have Kachuma again. So that's outreach for the month. Thank you.
Well, we only have these meetings once a month, so forgive me, Chuck, but like they say in court, Your Honor, since he brought it up, you're always correcting me. Let's solve this problem right now. Are we about to have a 70th anniversary next year or not? Didn't we start in 55?
A version of the club started in 1955, yes.
And it became SBAU at some point later. But I'm tracing this back. I'm thinking if we wait till the 75th, that'll be 2030, and I'm not sure how many of us can make it. But let's do a 70th and really give Diane Wilson back something to have to work on. Oh, well, we'll talk about it on one of the planning meetings. You did good. Thanks.
The conditional use permit here at the museum is very limited in how much we can do, but if we can, we should try to.
Oh, I could probably get Mayor Rouse to do a proclamation. One of our earlier members who joined in '72, who now runs the San Francisco-based, UC Berkeley. What's his name? Filipenko?
Alex Filipenko, 75.
He started with us, and he's one of those guys you see on the YouTube videos a lot. He would probably call in, if he can't be here, he might do a.
Get him as a speaker because his parents lived here, but they've gone now.
I wasn't thinking of a speaker. Just get him on the screens to say hi and thank you.
We could try.
Happy whatever anniversary. I think you did good. We can't do it without you, Chuck. I love you, man. Here is Diane Wilson back on her way up on the stage. As I tell you real quickly, next month, September 6th, our guest speaker on this very stage from what's called NEOWISE, which I guess is rotating or orbiting space telescope that uses infrared, is going to talk about hunting down dangerous asteroids that might want to kill us. Diane Wilson back, our events manager.
Thanks, Ron. I'm here to just, first of all, talk about the July 5th potluck, which was a big success. And I wrote up a little story in the newsletter, which maybe some of you have already read, but it was really fun. We had about 50 people there and just lots of food. And so we have another event coming up, October 26th. It's going to be at Kachuma Lake, and that's the camp out weekend. So we'll have a potluck where everyone will bring like a side dish or salad, and the club will actually purchase the main dish. So it's really important that you sign up so that we know how much to order for the main dish. So anyway, I'll have a little sign-up sheet at the bottom of the stairs here for any early birds. Thank you.
I forgot to give you the doctor's name, the professor, or he's from KPL, I think. That's Joseph Maciero is our speaker in September. In early October, a young grad student from UCSB will be up here. His name is Liam Brennan, and he's involved in some of the research they're doing out at the university on dark matter. And there's new stuff that he's going to tell us about. In November 1st, our speaker, I finally got her, the beloved Jen Ito, ITO, who is an astrophysics professor out at Westmont. Yeah, let's hear it for all of these speakers. Got my glasses down here, can't do without. In December, we have our in-house speakers. That means groups that are a part of us, and I'm looking forward to something from our astronomy connection to the City College, Mr. Kelly, Professor Sean, and also Bruce Murdoch will pair with Marshad Barnum.
Farshad.
Farshad, what did I call it? Marshad, okay, yeah. We're not drinking buddies yet, but maybe after tonight's speech. They're going to talk about N-bodies. This will be December, so you got plenty of time. And then I found a guy named Neil Malone. He's a captain, a pilot with Civil Air Patrol. He's in the club. I met him at Sandy's big party that they threw out there at Las Cumbres Observatory on May 2nd. He said, yeah, I'm a longtime member. Hasn't paid his dues lately, but when we find him, we're going to get the $20 out of him. $20, that's what you pay for a meal these days and a drink in Santa Barbara. You can afford it. Come join us. In any event, I don't see the president's face on screen, but I'm ready to bring on our guest. Actually, it's a lady that I've been dealing with for many years. She's got a doctorate. And ladies and gentlemen, it's going to be an interesting, not a really long speech, but one you probably have never heard before, at least this particular version of the topic. Dr. Nikolaus Volgenau is called Ethanol in the Ether. The man's primary responsibilities out at Las Cumbres Observatories in Goleta, global network of the telescopes, and they're improving the quality of their data, providing support for observatory users around the world. They have scopes with 1 meter or 2 meter wide mirrors in the back in every continent on the globe except Antarctica, I guess. The man got his doctorate in astronomy from the University of Maryland with a dissertation mapping the motions of dense star-forming clouds and the millimeter-wave emission from various molecules. Before joining LCO, Nikolaus spent 7 years at Caltech's Owens Valley Radio Observatory, where he was Assistant Director of Operations of the CARMA interferometer. And you'll probably want to go out having a drinking fest with a man. Sandy, would you like to introduce your man? Sandy Seal is Director of Operations at Las Cumbres Observatories, and is a big help for me. Where did she go? Aren't you going to introduce him? Well, I asked you if you wanted me just to give his bio. Well, then we don't have to sit through another long speech, Sandy. God love you. I will say I'll see you next Thursday night for Astronomy on Tap. Come on up here, Nikolaus. It's every Thursday at 3. It's in the backyard. 7:30, right? Very special. 600 watt. Dr. Nikolaus Volgenau. Thank you.
Thank you, Ron. Maybe one introduction is enough.
Nicholas,
All right, and now I need to pause for AV, right? Because we need to set this up.
You gotta get to share your PowerPoint.
You need me to go back to Zoom. You need this microphone on. And then you need to go to my presentation. No. Back to Zoom. think I'm set. I have a microphone in one hand, and I have a pointer in the other hand, and I have a laptop where I have to push buttons on. So 3 different devices to operate, but I'll do the best that I can. I'm very happy to be here this evening. Thank you very much, SBAU, for and I get applause even before the presentation starts. This is an easy crowd. I do need to emphasize something that Ron already mentioned, which is this is a reprise, if you will, of a talk that I gave back in March at an event called Astronomy on Tap. And Astronomy on Tap is a social and astronomical event that occurs monthly, hosted by Las Cumbres Observatory at M Special on State Street. And we do these regularly. In fact, if you like this sort of an event, an informal discussion of astronomy with alcohol included, then I encourage you to go to the Astronomy on Tap events, and there will be one next week on the 8th. And Megan Newsom, who is a graduate student at UC Santa Barbara, will be the speaker. She'll be talking about tidal disruption events, stars that get torn apart when they get too close to black holes. So a very exciting topic that she'll be talking about. I wanted to mention that not just to advertise Megan's talk next week, but also so that you know what my audience was for the talk that I'm about to present to you. In that I was giving a talk about ethanol in the ether, or alcohol in space, to an assembly of about this size of people who were drinking alcohol and probably had already had 1 or 2 pints by the time I was speaking. And so that's why that seemed like a relevant topic for that event. So I realize no one here has had a pint yet, but perhaps this will inspire you or something, or maybe encourage the SBAU to have an open bar next time. I don't know.
We can't sell alcohol on campus, so maybe for the next meeting.
All right, thank you, Rosina. So, in a room or in an open space with people who are drinking beer, this seemed like an appropriate way to start the talk. I'm going to be talking about alcohol in space. But I want to start with alcohol here on the Earth, and specifically what you drink when you are at M Special downtown, which is you drink beer, because they have many different beers on tap. Now, I am not a brewer myself. Perhaps some of you are brewers, and if that's the case, then you'll know many more details about brewing than I do. But I know the basics, and I want to start with the basics to let you know that when you make beer, even though there are different types of beer that have different ingredients, really basic beer has 4 ingredients. And one of those ingredients is a grain. You need some kind of grain, and typically that grain is barley. That's what's used for most beers. Sometimes you can use corn, you can use rice, it affects the flavor and so on. But you want to start with a grain, one of the essential ingredients. And what you do with that grain is you soak it in water. So the second important ingredient for making beer is water, and any brewer, again, will tell you the importance of good water when you're making beer. That's what's going to affect the taste quite a bit. You want to make sure you use good water. And so you put your grains, your barley, in your water, and of course, barley grains, those are essentially seeds, and when they get put in water, they'll start to sprout. They start converting the starch that's inside of them into sugars. And so what the barley turns into is what's called malt when it's placed in water. There's the fresh water that you want for your beer. And then after you have this barley malt, what you add to that at a later stage is yeast. And yeast is a living thing. Yeast is a kind of fungus, actually. And as a living thing, what it wants to do is eat. And what it does is it eats the sugar in that malt. And it does that to create energy for itself so that it can survive and make more yeast. And then the fourth ingredient in beers is hops. And hops is added as a flavoring ingredient. The malt that you create from the barley is very, very sweet. Like I said, it's producing sugar from the starch, so it's very sweet. And the hops you put in the beer to offset that, because the hops has the bitter taste. And if you have tasted hoppy beers, IPAs, pale ales, things like that, there's more hops in that, and that gives it the more bitter taste. But 4 basic ingredients for beer. Now, some of you might be saying, all right, the guy's already on slide number 5, and he hasn't mentioned alcohol yet. I don't see alcohol added here in the beer. Where does the alcohol get added? Well, that happens through a process called fermentation. Fermentation is what happens when the yeast is chewing on the malts, essentially, converting the sugar in the malts into energy for itself and also byproducts. So a way that I can describe what the yeast is doing is I can write it out in words, like this. So I can use my pointer now to show you that over here we have glucose. Glucose is the sugar. Glucose is the sugar that's created from the barley malt by when it germinates. And what the yeast does is it breaks that down into ethanol. Ethanol is a type of alcohol. That's where your alcohol comes from. And as it does that, converts it into ethanol, it also creates carbon dioxide. And then another byproduct is energy. And of course, that's what the yeast wants to do. That's what the fungus needs to survive. It needs that extra energy. So this is one way of describing what's going on in the fermentation process. Now let me introduce you to another way to describe this. And in this case, I can start with a chemical formula. There on the left is a chemical formula for glucose. C6H12O6. So I don't know how many of you have had chemistry or remember your chemistry, but what that means is there are 6 carbon atoms, C is for carbon, 12 hydrogen atoms, H is for hydrogen, and 6 oxygen atoms, O is for oxygen. So this is a chemical formula for glucose. And if I were to continue to write what's happening here, not in words, but with these chemical formulas, the yeast breaks that down into ethanol. One way to write ethanol is this C2H6O. That's ethanol. Makes 2 molecules of that, as well as carbon dioxide. Carbon dioxide you're probably familiar with, CO2. And then some extra energy. Energy is sometimes written as Q, sometimes written as H, sometimes written as E, like E equals mc squared is energy. But that's the energy that it then produces. So there's a second way to write down the fermentation process. And now I'm going to show you a third way. And this is going to be more pictorial. Here's a way that you can picture glucose. This is sort of the stick and ball model of molecules, which again, some of you may have seen in high school, your chemistry class at SBCC or something. In this case, what we're looking at here are representations of the atoms in the molecule. And the dark gray are these carbon atoms. So if you look, there's 1, 2, 3, 4, 5, 6. And the red are the oxygen atoms. There's 1, 2, 3, 4, 5, 6. And then the white ones are the hydrogen atoms. So this is a representation of the glucose molecule. And this is a way of thinking how those atoms are arranged in the molecule. You have to remember that atoms in a molecule are not actually solid balls attached by sticks. If you remember, an atom is actually mostly emptiness, with at the very center it has a nucleus, and in that nucleus are things called protons and neutrons. And then in this cloud around the nucleus are the electrons. And what happens when you make a molecule, these different atoms are connected by sharing their electrons. They're not actually sticks going through each other to connect them. They're sharing electrons. They're swapping electrons back and forth. And so that's what this model is intended to represent. But I'm going to show you a few more of these, which is why I wanted to introduce it to you now, this representation. So that's what glucose looks like. And then after glucose, like I said, that breaks down into 2 ethanol molecules and 2 carbon dioxide molecules, which look like that with this ball and stick representation, and then extra energy, which is a little burst of flame. for the yeast. So 3 different ways to describe this process. So continuing our basic chemistry lesson, I mentioned that the ethanol is an alcohol. That's the kind of alcohol that is in beer. That's the kind of alcohol that we can drink. What is an alcohol? Well, for a chemist, an alcohol is basically a molecule where you have a carbon atom, again, C is the carbon atom, attached to a hydroxyl radical. And the hydroxyl is the oxygen and hydrogen together. So the very simplest kind of alcohol you can have is called methanol. And this is that ball and stick representation of methanol. In this case, you can see the hydroxyl, which is the oxygen and the hydrogen here. And then this is this methyl group right here, the carbon in the middle and the 3 hydrogens. Simplest alcohol right there. But of course, it is possible to build more and more complex alcohols. And the second most complex alcohol is ethanol, the one that I was just describing on the last slide. So here's 3 different ways to represent ethanol with a chemical formula. So the C2H6O is one representation. You also often see it written C2H5OH with a radical out on the side. And then you sometimes often see it written like this, with 3 different sections. And the reason you might do that is because that makes it look a little bit more like what the molecule actually looks like, right? You have the hydroxyl radical up here, and you have an ethyl group there, and you have a methyl group out here. So that is this ball and stick representation for the ethanol molecule. Some people who have more imagination than I do look at that molecule and they think it looks a little bit like a happy puppy. So if you can imagine that the oxygen molecule up here is the head of the dog and this is its snoot, and here are the front 2 legs and here are the rear legs, but it's so happy that it's sort of hopping up on one leg or the other. That's the happy puppy molecule. So an easy way to remember what the ethanol molecule looks like. More complex than ethanol, you add another ethyl group and you get to propanol. And here's the representation of propanol. You add another one, and you get to something called butanol, and so on, and so on, and so on. And there are different longer and longer chains with these different ethyl groups for more and more complex alcohols. So that's an introduction to the chemical formulas there. So as I mentioned, the ethanol in your beer comes from this fermentation process where the yeast works on the glucose. And the way that a brewer could monitor how much alcohol is in the brew that they're creating is by measuring essentially the density of the liquid that's produced. Because initially, the liquid malt extract, which is called wort, is more dense than water. But the ethanol that's produced by the yeast is less dense than water. So as you let this fermentation process continue, more and more alcohol is added, and your liquid will get less and less dense. And so brewers do this, they measure something called, what is essentially the density of the liquid, what's called a specific gravity. And of course, this is a process that for industrial brewers, commercial brewing companies, they have this down. And it's not something like they need to dip into the vat by hand or anything like this. They have this fully controlled. But that's how they measure the alcohol in beer here on Earth. Well, I forgot. I forgot my animation. I forgot to start my animation, but I'll let you see the transition I'm about to make. And back. From the light brew to the reddish brew to the dark brew to the telescope tube. Because what I wanted to show you next is about making the step to alcohol in space. From how we have, what we understand about alcohol here on Earth, the fermentation process, to alcohol in space. And the specific questions that I'm going to try to answer for you in the next few slides are these. First of all, how do we detect ethanol in space? How do we know it's out there? Where do we look for it? And then why do we look for it at the end? So first of all, the how. And here there are 3 things I'd like to get across, again, continuing my sort of basic chemistry lesson. First of all is that molecules are basically groups of atoms sharing electrons. I mentioned this when I introduced the ball and stick model. You have these atoms close together, they're sharing electrons back and forth. That's making these electronic bonds between them. So, and this is an example using the ball and stick model. Again, this is ethanol. Second thing to note is that when these molecules are free-floating in space, then those atomic bonds between the atoms, they can move. And they can move in several different ways. They can vibrate, they can twist back and forth, they can bend. I'm doing this with my arms now, but, and they can rotate. And so here is again a ball and stick representation of one of those motions. In this case, this is a vibration. The atoms in the center moving in and out, the ones on the outside rotating a little bit as they're affected by the charges of the protons and electrons. So it's that type of motion that you can imagine for a vibration. Here is methanol again, so this is the simplest alcohol. And this is showing a number of the different motions. It sort of cycles through the different motions that can happen, the different vibrations, and the different, some of the bending modes, and so on. So these are examples of how simple molecules in free space can move. So that's the second lesson. The third, the thing you need to know is that each specific motion that I just described, a vibration, a bending, or a rotation, each of those specific motions is associated with a specific energy. And that's really the key to detecting these things in space, is knowing that specific motions in these particular molecules are correlated with specific energies. And so I'm going to try to introduce you to this further by really simplifying things, going to a simpler molecule. Rather than ethanol, and even simpler than methanol, I'm going to simplify things even further to just show you a carbon monoxide molecule. So a carbon monoxide molecule is just one carbon atom in the gray and one oxygen atom here in the red, bonded together. It does away with a lot of the extra motions. You don't have a lot of bending and things like that. And the simplest type of motion, the lowest energy type of motion that you can have in a carbon monoxide molecule like this is rotation. It can rotate end over end. You can imagine it tumbling. And that's the lowest, takes the lowest amount of energy to do that sort of motion. And here's a little animation that I've embedded here. But it can't rotate at just any speed. That rotation, like I said, is specific rotations take specific amounts of energy. So transitioning from one amount of energy to another amount of energy takes a specific, will affect the amount of rotation, the rate of rotation. And what this animation is showing, when it starts out and the whole background is gray, it's rotating faster. And then you'll notice at some point it rotates slower, but what's emitted in the green is the energy. So you're liberating energy, and because the energy is going out of the system, that carbon monoxide molecule slows down a little bit. And that's what this animation is intended to show. Now I'm going to move it over to the left, and I'm going to move it over to the left because I want to make room for this information. So what this is showing here is, again, the rotating carbon monoxide molecule on the left. And this here is what's called a rotation ladder. And it's just intended to link the different rotation states of a simple molecule with the energy that corresponds with a transition between higher energy and lower energy. So in this case, the J is the symbol for what's called a rotation quantum number. And all you really need to know is that 8 is larger than 7. So that means that 8 is faster rotation than 7. 7 is greater than 6, faster to slower, faster to slower, faster to slower, 5 to 4, and so on. So each of these is a rotation transition in the carbon monoxide molecule. Each one of those transitions is slowing down, and when it does that, it emits energy, follow the rung of the ladder across, at a specific frequency. And these numbers here are just showing you, sort of giving you a calibration for the amount of energy. Energy in the form of light has characteristic wavelengths or characteristic frequencies. You can think of it either way when light is emitted. So that's why on the same scale you can include a frequency, which is how many wavelengths pass you at any second, or a wavelength, which is how long it takes for that energy essentially to cycle through a full wave. So either these are equivalent ways of describing the energy that is emitted. And what I wanted to show you here is for these low rotational transitions, down to the fundamental rotational transition, approximately what the wavelength is of the energy, to give you an idea of how much energy we're talking about, whether this is visible light or something else. So if you look on the far right column, I've included the wavelengths. And the wavelengths vary from down here at around 100 gigahertz, you have a 5 millimeter wavelength, to 3 millimeter wavelength, to a 1 millimeter wavelength. Up here at 600 gigahertz, you're at a half a millimeter wavelength. That's the characteristic wavelength of the energy that's emitted when these carbon monoxide molecules slow down. And to help you calibrate where that is, if you're wondering where is visible light, what's the sort of radiation that I can see with my eyes, that would be way off the top. That's way off the top of the scale here. Visible light has a frequency of around 500 terahertz, not gigahertz, which is pictured here, or a wavelength of about 500 nanometers is usually what we talk about. A nanometer is a billionth of a meter. Or I wrote it down here, which is a little bit obscured, in millimeters. It's 0.00005 millimeters, which is 10,000ths of a millimeter. Very, very small wavelengths. Those are the sort of things that you can see with your eye. This sort of radiation from simple molecules is not what you can see with your eye. So this is the radiation we're looking for to see these molecules in space. What sort of telescopes do we use? Well, here are some photographs of the telescopes the Las Cumbres Observatory has over here on the left. A 2-meter diameter mirror is in the bottom here. This is one of our telescopes in Texas with a 1-meter diameter mirror. Here's a 40-centimeter diameter mirror on the bottom. This one's on Tenerife. And here's one of the Gemini telescopes. This one's on Hawaii. That says an 8-meter mirror on the bottom. So different sizes of telescopes, but all of these have essentially cameras, optical cameras on them. And so they're sensitive to optical light. And as I just mentioned with the last slide, that's not really the sort of radiation that you're going to get from these simple molecules. That wavelength is much, much too small. Optical light is much, much smaller than the rotational wavelength that you're getting from these simple molecules. So you need a different kind of telescope, and you need a telescope that has receivers that are sensitive at millimeter wavelengths or sub-millimeter wavelengths. Like I said, half a millimeter, a quarter of a millimeter, that sort of thing. And so this sort of work is done with telescopes like this. Over here on the left, the GBT is the Green Bank telescope. It is in Green Bank, West Virginia. It has a dish diameter of 100 meters. So this is a soccer field inside here. And then the receiver is up here at the top. And that's where all of that radiation coming from space is reflected up into there. Here on the right is the Iran 30-meter telescope. This is 30 meters across. It's in Spain. I just mentioned there. Dish diameter, 30 meters. And it's sensitive to wavelengths from about 3 millimeters to 0.8 millimeters. 800 microns. And then where a lot of this work is happening now with one of the best telescopes in the world right now is with ALMA. ALMA is the Atacama Large Millimeter Array. It's in the Atacama Desert in northern Chile. And this is a photograph of just some of the dishes in this array. In total, there are 66, 54 with 12-meter diameter mirrors and 12 of them with 7-meter diameter mirrors. So very large telescopes, and many of them, with these receivers that are sensitive from wavelengths from 9 millimeters to 0.3 millimeters. These are the sorts of telescopes to think of when you're thinking about who is looking for molecules in space and with what instruments. So that was a little bit of answering the question of how, right? The specific wavelengths that we need to look for because of these rotational transitions and vibrational transitions, and what sort of telescopes we need. The next question is, where in space should we look for these molecules? Now, many of you are astronomers with your own telescopes, and you're looking up at stars in the sky, and stars are common objects to look at, and you probably know that there is, stars do form more complex materials. They're mostly hydrogen, but they're forming heavier and heavier elements. Our sun goes through nuclear fusion at its core, and it fuses the hydrogen into helium. More massive stars at their cores can make heavier and heavier elements. So it's more massive stars that provide carbon in the universe, and nitrogen, and oxygen, and magnesium, and silicon, and iron, and all of these heavy elements. Some of them form in their cores, some of them are created when the star explodes at the end of its lifetime. And we know that the heaviest stars, the most massive stars, I should say, explode at the ends of their lifetimes in supernovae. And when they do that, they liberate that material. That material gets distributed out into space. And so you might think, well, if we can make things like carbon and nitrogen, oxygen, and I know that carbon and nitrogen, oxygen appears in these simple molecules, well, maybe they make these simple molecules too, and then push them out into space at the end of their lifetimes. But there's a difficulty with that, and that is that the stellar temperatures are really too high. It is possible in the atmospheres of some stars, especially the lowest mass stars and the coolest stars, to make some simple molecules. We do see them there on the outer layers in the sort of chromosphere, photosphere area. There's some very simple molecules. But the more complex molecules with multiple atoms, the sorts of things I've been introducing you to, like ethanol, those sorts of things would be disrupted by the heat, by the radiation on the surface of a star. And so you couldn't form those sorts of things there. Well, if they can't form on hot things, these complex molecules, what about on cold things? Well, space is cold, but most of space is empty space. Are there places in space that are cold, but where you have stuff? And the answer is yes. And this image here is an example of a glob of material, a dark cloud in space. This one specifically is called Barnard 68. That's from a catalog by E.E. Barnard. Some of you might know Barnard's star and have observed Barnard's star. Barnard also put together a catalog, and this was the 68th object in his catalog. It was also cataloged by Beverly Linz, and it was the 57th object in her catalog. And it looks like a hole in space. With this view. It looks like, oh, there's a whole bunch of stars here, but there's some particular line of sight where there are no stars. I wonder what's going on there. Well, what's going on there is that the starlight from the stars behind it are being blocked. There's some very dense material here, and the material I'm talking about are dust grains and gases that are here. And it just hasn't produced, it's an area that hasn't produced any stars, so there's nothing in there to make it luminous, but it is blocking the starlight behind it. And I have some information about this one here. It's a dark cloud. It's in the constellation of Ophiuchus, which many of you may know. Distance of about 400 light years and about half a light year across, and it's very cold in there. This is 15 Kelvin, so 15 degrees above absolute zero. But it's the sort of environment where we can see with an image like this that there's gas and dust there. At the center of that, it's denser than empty space, and it's at the center will also be shielded from ultraviolet radiation and other radiation from surrounding stars. So this is the sort of place we could look. And these sorts of objects in space are what constitute what's typically called the interstellar medium, or the ISM. And the simplest definition from my Astronomy 100 textbook from years ago, what is the interstellar medium? It's the stuff between the stars in the galaxy. We're accustomed to thinking the galaxy is this collection of stars and bright nebulae and things like this. But these dark nebulae, these clouds of gas and dust in space, that's the stuff between the stars, that's the interstellar medium. Here's another one that you might be familiar with. This is Barnard 33, most commonly known as the Horsehead nebula for obvious reasons. That's an Orion. So this sort of material in space, in something like Barnard 68 or Barnard 33, it looks dense, it blocks the starlight, but the material in there, even though an astronomer would call this, a dense gas in space, it's actually more rarefied than the highest vacuum that we've achieved here on Earth. And this is the sort of site where what's called gas phase chemistry can happen. So these atoms that are floating around in space, the carbon and the nitrogen and the oxygen and the hydrogen, the sort of things that I've already mentioned, can bump into each other and perhaps form molecules. And in fact, they do form molecules. And so I'm going to talk you through just a few of the simple reactions. The most common element in the universe is hydrogen. Most of what's out there that is stuff is hydrogen. And so what that means is in a dense environment, like one of these Barnard clouds, the most likely thing that any other atom is going to bump into is hydrogen. And here's an example of that. We're going to start with an oxygen atom. An oxygen atom that was formed much longer ago in some star, but it's now in this dense cloud of material and it bumps into a hydrogen atom. And if it bumps in just such a way that it can combine and make one of these electronic bonds, then it's going to form an OH radical, that hydroxyl radical that I mentioned before. And if it bumps into another hydrogen, well then you have H2O. And H2O, as everyone knows, is water. So you can form water in space through this gas phase process. What about if we start with a carbon atom? We start with a carbon atom with C, and it combines with an H, and it combines with another H to form CH2, and it combines with another hydrogen to form CH3, and ultimately you can get to CH4. Carbon typically forms 4 bonds when it's stable, so you form CH4. Does anyone know what CH4 is?
Methane.
It's methane gas. That's right. We know it here on Earth as a greenhouse gas. So methane can form in space. What about if we start with that carbon monoxide that I introduced you to earlier? Well, it collides with a hydrogen, forms HCO. Collides with another hydrogen, can form H2CO, that's formaldehyde. Combines with another hydrogen, you get CH3O, and ultimately you get CH3OH when it combines with another hydrogen. CH3OH, does it look familiar? CH3OH is the first alcohol that I introduced you to, that's methanol. And I put a little poison bottle there because it's not ethanol, it's not the kind of alcohol that you can drink. Methanol is commonly called wood alcohol, and it's not the kind you want to drink. But you can form that in space. But it turns out forming even more complex molecules is very difficult in the gas phase. And so astronomers, starting already decades ago, postulated that there must be some other way to form molecules, complex molecules in space. And the solution appears to be chemistry on the surfaces of grains. Well, what are grains in space? Dust grains. The heavy elements that are formed in stars, like silicon and magnesium and iron, they readily combine. They don't stay loose. Whenever there's anything else around, they will combine with them to form these dust grains of silicon oxide, silicon dioxide, olivine, to form little clumps like this, and there's no measurement tab on here, but this is just a few microns across, so a few millionths of a meter across. And they provide on their surfaces places where chemistry can happen. So atoms can combine on the surface of this, and then if radiation comes along, can release them back into the interstellar medium, and that's called grain surface chemistry. And it's this sort of chemistry that we think has given us the more complex molecules in space. It has to happen, though, in a dense, dark environment, shielded from a lot of radiation, so away from the hot stars. And where this can happen is in something like Sagittarius B2, which is the next object I'm introducing you to here. Sagittarius B2 is a very large, very dense, dark cloud near the center of the galaxy, at least from our point of view towards the center of the galaxy. And what I show here on the right is an image towards the center of the galaxy. And this is actually very large. This is several degrees of the sky. But those of you who are avid sky watchers might know that this is sort of towards the center of the galaxy, towards Sagittarius A star. And Sagittarius B2, this dark cloud, is this area here, roughly centered on that purple cross. And I think, as I press this, we should gradually zoom in. There we go. So we're zooming into that purple cross where Sagittarius B2 is. And you can see there's all this dark material where you would expect towards the center of the galaxy, the density of stars to just increase and increase and increase. And you get more and more stars, you get brighter and brighter and brighter. Instead, you're seeing a lot of darkness here. It still looks like a lot of stars, but these are all stars that are in the foreground. All that darkness that's behind there is starlight from more of the galaxy that's being obscured by the Sagittarius B2 cloud. But it's very large and it's very dense, and that's why it's the perfect place to look for complex molecules, including ethyl alcohol. And so now let me introduce you to the discovery paper of ethyl alcohol in space. That's right, ethanol was discovered in space. This is a paper from 1975 by Benjamin Zuckerman and colleagues announcing the detection of interstellar trans-ethyl ether. And this paper includes some of the things I've already shown you, a little diagram of what ethanol looks like. This is the happy puppy dog again, with the snoot here and the head there, and there's the forelegs and the hind legs and so on. The trans, this particular formation, it also shows the rotational energy levels. So this is a different way of showing that rotational ladder that I introduced you to a few slides ago. In this case, the rotational quantum numbers are here along the bottom, and they're pointing out the particular transitions that they detected, and also what the frequencies are. I thought they were there in the caption, but they're not. They do list them in the paper, of course, that they have detected. And so part of this paper, you can tell that they're very proud of their discovery, because you look in the text of this paper, and they say, we detected a truly astronomical source of ethanol alcohol located in the general direction of the center of the galaxy. And they get a little bit cheeky beyond that. They say, preliminary estimates indicate that the alcoholic content of this cloud, Sagittarius B2, if purged of all impurities and condensed, would yield approximately 10 to the 28th power fifths at 200 proof. This exceeds the total amount of all of man's fermentation efforts since the beginning of recorded history. It's a great paper. It's not the sort of thing you usually read in a scientific paper. But it's the sort of thing that made me wonder, well, 10 to the 28th power fifths. I have no concept of that number. What does that even mean? So I'm going to introduce you to a little bit of math. So the first thing I need, of course, we're in a bar. We're talking about alcohol, so I need a cocktail napkin. Here's my cocktail napkin. I'm going to say 10 to the 28th power fifths. Well, how much is that? Well, 1/5 is 750 milliliters. So I can convert my 10 to the 28th fifth to liters. That means the total volume of alcohol, 7.5 times 10 to the 27th power liters. Still a big number that I can't really grasp. Of course, I drink my beer in pints. And if I convert it to pints, I can describe that as 16 octillion pints. And you get to octillion by going, million, billion, trillion, quadrillion, quintillion, what's next? Hexillion, septillion, and then octillion. Or if you prefer, 16 octillion pints is 16 billion, billion pints. That's how much alcohol you have in Sagittarius B2, according to Zuckerman and colleagues' estimates there. Okay, that's a lot of alcohol. How much volume is it distributed over? Well, how big is Sagittarius B2? Let's try and get a grasp of how big Sagittarius B2 is. So another cocktail napkin. If it's a sphere with a diameter of about 160 light years, well, that means its total volume, if I think it's a sphere, is 2 times 10 to the 60th power cubic centimeters. Again, 10 to the 60th power, I can't really conceive of that. So let me see if I can compare it to the solar system. How big is the solar system? If I consider the solar system out to about the orbit of Neptune, and I think of that as a sphere, it's not really a sphere, it's more disk-like, but if I think of it as a sphere, how many solar systems is that? Well, the volume of Sagittarius B2 cloud is about 2 quadrillion solar systems. Very, very big. Okay, so I'm not going to be able to get all that alcohol. I'm not going to be able to get over all that space. What if I just wanted 1 pint? I just want 1 pint of this super Sagittarius B alcohol in order to, make my Sagittarius brew or whatever. If I just want 1 pint, I've got to collect all of the ethanol molecules within a volume of about the orbit of the moon. You can have some idea of how far away the moon is. It goes around us in a month and so on, but you have to get every ethanol molecule in that volume in order to fill your pint glass. Trying to give you some idea of these big numbers. So, Sagittarius B2 cloud has developed a new nickname, and the reason it's developed that nickname is because a lot of these complex molecules have been discovered there. It has the right conditions, it's cold, it's dense, it's large, and so it has this nickname of the large molecule high amount, or LMH sometimes. More than 250 molecules have been discovered there, complex molecules with up to 20 atoms, and then including this C60 atom, sometimes called a Buckminster fullerene, looks like a soccer ball. And some other interesting things that have been discovered there are formic acid. Formic acid is a simple molecule. This is the formula right down here, HCOOH. Is interesting because it's something you can smell and taste. It has a citrusy taste and smell. And ethyl formate has been discovered there, C3H6O2. And ethyl formate is something you can smell and taste. It's what gives raspberries their taste, and it has sort of a rum smell. And when these molecules were discovered, it led to several articles in the popular press, for example, The Guardian, that the galaxy tastes of raspberries and smells of rum, which is great for the popularization of science. I don't know if you could actually send anyone out there to verify, because it's quite far away. But that's the ethyl formate that's in space, and it's made it into popular texts as well. The Milky Way smells of rum and raspberries, and other amazing cosmic facts available for you to read. So that's Sagittarius B2. Like I said, that's closer in towards the galactic center. What about something that's a little closer to home? Well, there's the Taurus-Origene complex, which is closer to us, relatively, a distance of about 450 light years. That also contains hundreds of young stars with disks and planets sort of embedded in this cloudy material. That's called the Taurus molecular cloud. And I would love to show you this image of it, which was made by the Herschel Space Observatory. This was made in infrared radiation and submillimeter radiation. The wavelength range is right down here. And at these wavelengths, well, this dark dust, what usually obscures starlight behind it, actually radiates. And so you see this dense cloud radiating in this infrared and submillimeter emission. And you see these sort of string of pearls sort of structures in here, and some of these brighter nodules there are where stars are forming. Stars are forming in these small embedded protostellar clumps here. Another thing you'll notice, and that's the last bullet point that I put down there at the bottom, is this is not a spherical cloud. I was talking about Sagittarius B2, estimating its volume like it's a big sphere, and you sort of think of clouds as roughly, big roundish clumps, from The Simpsons or whatever. But they're actually long filamentary things like this. And so this is one that's a little closer to us. And this is a sort of place where we would search for these molecules in space, and do search. So the last question I said I would address, and this is just the last few slides, is why do we search for ethanol? Why are we looking for this? And what's not a reason is to make some sort of commercial product from this search. So it's not to provide a source of consumable alcohol for us here on Earth. I don't think anyone would be able to have the technology or go through the expense to actually bring in this alcohol and create their own brew and sell it to, the billionaires of the world. So it's not that we want to get to that alcohol. It's more that by detecting that alcohol or these other complex molecules in space, it tells us something about the physical conditions in that place in the universe. So if we see particular transitions, that is particular radiation, which we know corresponds to particular energies, we can say, oh, I know that where this molecule is emitting from, that material has to be in this temperature range or in this density range. And it gives us a probe of what the material is like, where those molecules actually are. And it allows us to explore some of these questions here to try and figure out how complex can this molecular chemistry get, and is it possible for these complex molecules to be delivered onto forming stars, onto forming solar systems, forming planets. And a reason that's interesting is because as you get to more and more complex molecules, these complex molecules become the building blocks for things that are required for life. The complex molecules that you need in order to form amino acids, for example. So my question here at the top, can the cold universe make nucleobases? And nucleobases are some examples of those, of these structures here. These are those ball and stick models. They show you the same sorts of atoms. So this is carbon, blue is nitrogen, white is hydrogen. These are 4 different types of what are called nucleobases: uracil, cytosine, adenine, and guanine. And those of you who maybe had a basic biology class or a little bit of pre-med or something like that might recognize these. I wasn't going quite that far. If I illustrate these in a different way, so I have a different figure here now. Here are the same 4 nucleobases, but now they're illustrated in a little bit different way and color-coded. Blue and green and yellow and orangey red. I can then put them together like this, and again, the blue and the green and the orangey red and the yellow are the nucleobases that form the central parts of RNA, so ribonucleic acid. And this, ribonucleic acid, and DNA, as someone here in the front row just said. Exactly, instead of the uracil, you need thymine, yeah. Are some of the, are essential for life. Any living organisms have RNA and DNA in them. And so the question is, can these things actually be formed in space and then delivered to nascent planets, planets that have atmospheres? Like I said, nucleobases make amino acids, and amino acids make more complex things like proteins, and proteins are necessary for life. We have discovered these nucleobases in asteroids. Here is a recent paper, 2022, identifying the wide diversity of extraterrestrial purine and pyrimidine nucleobases in meteorites from here on Earth. The purine and pyrimidine, the 4 nucleobases that I just showed you, 2 of them are purines and 2 of them are pyrimidines, I can't remember which, but it's essentially those nucleobases that they've discovered in meteorites seen here on the Earth. And that's the ball and stick models of those. So these sorts of questions have led many astronomers, did lead astronomers a few decades ago, to explore whether it's possible to detect the simplest amino acid in space. The simplest amino acid is glycine, and this is the ball and stick model of that. Again, atoms that you recognize in there. This is the formula right here on the right. The simplest amino acid, and is it possible to discover this in space? Because if this could be formed in space, this is the sort of thing that if it is delivered to, for example, the young Earth or another planet with a suitable environment, could that trigger the origin of life? And so a lot of effort was made to search for this, and in 2003, a paper was published announcing the discovery of interstellar glycine. And from that paper, they are also very proud of their discovery. They said, if more complex organics, such as amino acids, exist in interstellar space, then they may have jump-started prebiotic chemistry on the early Earth. Fantastic discovery. And it also brings about one of the great aspects of science, which is that any claim that you make should be verified, right? Independent scientists should verify that discovery. So as soon as this was published, a whole bunch of other astronomers using those sorts of telescopes that I showed you earlier went to verify this interstellar glycine, including many researchers who had done this sort of work before, because they questioned whether glycine had actually been found. This is a paper by actually some researchers that I know a rigorous attempt to verify interstellar glycine, and their conclusion was that this was not glycine. They did not discover glycine. They say their key lines, that is the specific energies, fail the tests required for correct glycine identification. In investigating alternative identifications, we find that the carriers of several important spectral lines that have been assigned to glycine are more logically assigned to other, more common species. And so they said, no, it's not glycine, and many other astronomers, astrochemists, people that do this sort of work, also are of the mind that they did not discover glycine. But the search continues. And here is a recent paper, 2022, a laboratory detection and astronomical study of a glycine isomer. It's not glycine, it's a glycine isomer. An isomer means it has all the same atoms, it just has a different structure. So it's not the same thing. A deep search for glycine conformers in Barnard 5. A conformer is an isomer with a twist. It has an extra change in its orientation. So again, it's not exactly glycine. They looked for it in a dark cloud, Barnard 5, and I'll give you the result, they didn't find it. Glycine isomer detected in the interstellar medium, glycol amide. Again, it's not glycine, it's a glycine isomer. This is a paper from last year. A laboratory study of glycine formation. They say, they try to replicate the formation mechanisms in the lab in a study. They say, all you need is carbon monoxide, formaldehyd, and water, and you can make glycine in space. It should be out there, but we're still looking. Here's a paper from just last month. Detection of possible glycine precursor molecule, methylamine, towards the hot molecular core. Again, one of these dense clouds. In this paper, they say right at the beginning of their abstract what kind of search this has been, what kind of effort this has been. The search for the simplest amino acid, glycine, has become a never-ending story for astrochemistry and astrophysics researchers. In the last 40 years, all searches for glycine in the interstellar medium have failed. But the search goes on, because it's still possible that it's out there, and it's very, very interesting if it is. And so there's still many places that we can look, many environments that we can look in, and it's very, very tantalizing to consider the possibility of glycine or other molecules like it to be delivered to forming planets that have atmospheres that are conducive to the formation of life. So this is a very active study of research. It's something that's still supported by NASA, and that's why I included this image here, which is a conceptual image from NASA showing these molecules being delivered to a planet that is just forming, being bombarded by asteroids and then being formed, and speculating on the possibility that the building blocks for life are being delivered from interstellar space. So I hope that this work continues, and thank you very much for your attention.
We have a microphone up front here, Barry.
How about our distinguished city college professor?
Yeah, I got a question, actually. Can you give me some insight about why the dust grains are the limited types of dust grains you mentioned? I don't know why there would be just that limited type. I kind of expect almost anything to form dust grains if there's material there. Like in the solar system, I would expect to find lots and lots of different materials.
That is the case, yes. I guess the other materials, so you're thinking like the carbons and things like that, are also reactive, are also in the gas phase. What we know about the dust grains is things like magnesium, things like silicon. That's where most of it goes. It gets frozen out into these dust grains. So the dust grains that we see in the signatures that we see from observations like in the infrared, like the Herschel map of the cloud that I showed. The signatures of dust grains that we see in there are typically magnesium and silicon and things like that. And we then infer the presence of other types of grains from that.
So you're not saying that they're not there, they're just not the signatures that you're seeing.
That's right.
I see water grain signature, or I wouldn't see that.
Well, water would freeze into ice, right?
Right.
So
But dust grains could be, like, why does it have to be those dust grains that the chemistry takes place on? Wouldn't any dust grain be suitable?
That's a good question. I think that the lighter elements are likely to be more reactive, to be involved with the reaction, whereas these olivine and silicon compounds and so on are less likely to react than with the individual atoms that are sort of migrating on the surface. But I'm definitely not an expert in that field.
Over here?
Yeah, this is before or after. We know that our life is based on carbon-based, carbon-based.
So that's organic chemistry, essentially, carbon-based chemistry, right?
You indicated also that silicon is active. And there's a possibility that silicon-based compounds will form different kind of parts. Can you speak to that in any way?
Can you repeat that question?
So the question is whether you can have silicon-based chemistry rather than carbon-based chemistry. And I think the answer is yes. But silicon is far, far less abundant in space than carbon. And so you're much more likely to produce these carbon compounds. And it's also much more likely to, the energies that are involved, you're much more likely to form these bonds between the more abundant carbon and these other atoms.
There's a question back here.
I have a question. The ethanol that you're talking about, it's being created in space by the pumping out of all of the molecules.
Yes.
Is it a gas or is it liquid, or is it just so particularized that it's not quite liquid yet? Because it's here, it's liquid.
Repeat the question.
So the question is whether the ethanol that is detected in space is in gas or in liquid form. Is that right? And it's so rarefied that it's essentially a gas. These are individual molecules we're talking about. They're not so dense that it's a liquid ethanol.
Okay, so in order to get that pint that you're talking about, then you have to just get them all together in one glass.
Exactly. Yeah. We're really talking about, in that example, picking individual ethanol molecules and putting them in the glass one by one. There's no liquid out there that we can gather like that. Oh my goodness. Am I picking?
I've got the microphone.
Your job, Rob.
I've got the microphone right here with one person, so
Oh, you got the microphone. Okay. You're asking the question.
Yeah, is there any indication of catalysis on the dust grains, maybe from the iron?
Again, not my area of expertise, but yes, there are other essentially surface chemistry processes that can happen, especially if the dust grains are in radiated environments. Is that what you're talking about?
Well, I was just thinking there's such a small amount of energy available, it seems like you'd need some catalysis.
Okay. I don't know the answer to that. Sorry.
Who else wants to get the microphone? Is there any sense of the preponderance of ethanol
versus something like methane or any other kind of smaller molecule you're talking about?
Oh, the smaller molecules are generally more abundant. The things you're more likely to form, like methane, are much more abundant than ethanol. Ethanol was just sort of the hook for this talk.
Right, but so in that 70s 5 paper,
Yeah.
they gave an estimate of how many molecules or some sort of concentration, right? Which would be very small, I assume, because you're in a vacuum. But what would ethanol versus methane be? Like 1,000th of the preponderance or something, or is there any?
Far less than 1,000. Yeah, methane would be far more abundant than ethanol. Yeah.
In terms of grain surface chemistry, when I think of the formation of biochemical molecules, particularly in plants and animals, it's often facilitated by enzymes. Would you say that the grains act as a substrate similarly to an enzyme in space to facilitate bond formation? Because I mean, at like such a rarefied density, from like a statistical mechanics point of view, it seems really unlikely that those molecules would form otherwise, I guess.
So here's what I can say to that, which is my area of expertise is more in the free-floating molecules rather than the grain chemistry, which is how I've had to answer several other questions. I do know that the grain surface chemistry, that the word substrate is used to describe the grain surface chemistry. Essentially, the grains provide the substrate for these reactions between atoms, and what they help do is essentially absorb the energy when the atoms combine to form molecules. If you imagine these things happening in free space, for one thing, it's more difficult to get the atoms to hit at exactly the same time, essentially, to form these complex molecules. And secondly, sometimes the energy of the formation is too great of the collision that they can't actually combine. And by having these atoms essentially roving over the surface of a grain until they meet, that extra energy doesn't affect those individual atoms. So some of that energy can go into the matrix of the grain. Your last thing that you mentioned was an enzyme, and honestly, I don't know what an enzyme does, what its function would be in this case. So.
Bruce, give it to Bruce. Bruce Murdoch, ladies and gentlemen, of the Santa Barbara Theater Orchestra tonight. He's in our club. He's the president of
My comment goes back to making beer, because I've done a lot of that. And you've mentioned that they put the hops in to kill the sweetness. That may be one of the effects, but the principal use of hops goes back a long time. And, you know, in jolly old England, they didn't have refrigeration. You draw a beer, it was at room temperature and room pressure, and they had a pump on it. And the purpose of the hops was a preservative, so it wouldn't go bad. And it also does impart various flavors, and then you get all kinds of people that make their various kinds of beer with special hops and whatnot. But its basic purpose, when, you know, they used to pay the Roman soldiers in beer. And it goes on back for a long way.
I've heard that, yes.
Yeah. So anyway, the main reason for the hops was the preservative.
I defer to your expertise. I am not a brewer. What I know of brewing is essentially what I related, and I really wanted to get to the topic of fermentation because that let me introduce the ethanol.
Well, actually, making beer is a pretty traditional making almost all of the alcoholic beverages we have. They distill it.
Sure. Yeah, I could have chosen a different beverage, I suppose.
Go ahead.
In planet formation, is this the only source of those molecules that land on the planet, or do they form within the planet once the planet's forming as well?
Well, you know, on Earth we have biological processes, of course, that give us complex chemistry as well. There's a very famous experiment, the Miller-Urey experiment, right, where they took sort of the basic elements, the basic molecules that were around in primordial Earth, and they added energy to simulate like a lightning blast, and to see whether energy with these basic compounds could create complex molecules. And that experiment essentially verified that you could form these complex molecules in that way. The question really for astronomers is it also possible that these molecules were created either in free space or on the surface of grains, on the surface of asteroids or whatever, and then when a planet is formed, that those materials are part of the formation process and then survive whatever volcanic eon happens in the early formation of a planet. Whether that can, if those survive, then they can still be there in order to begin organic chemistry and the creation of amino acids and things like that later on. Does that answer? Okay.
Other questions? And those four compounds, glycine, cytosine, they're the four little things on the rungs of the ladder inside the double helix, right? Different combinations make different animals, different people, different diseases if they're lined up wrong. Is that true? What was the amino acids?
What I showed are the rungs of RNA. So it's a single ladder, a single helix. The double helix is DNA. And as this person here in the front row pointed out, one of those nucleobases is different. Rather than uracil, you have thymine.
But I've always heard it's four lined up on the rung, right?
It's 2 and 2, right? There's always 2 that match,
Two on one
adenine
side,
and
two
thymine.
on- Is there anything special in the rungs that go around that make the helix, the double, or just the ladder, the little rungs in the middle?
Oh, what I was showing, the nucleobases are the rungs of that ladder. That's right.
What makes up the outer part, the part that swirls around and becomes one of those, what do they call those staircases that you go up?
Right. I think in my figure it was labeled as a phosphate backbone. Definitely not my area of expertise, so I've got to refer to someone who's had a few more biology courses than I've had. Oh, there.
Okay, tell me.
Basically a nucleotide, on one side you have what makes it unique, and then on the other side you have the phosphate backbone, and so the phosphate backbones of several nucleotides will like stack on top of each other and form one half of your double helix, and on the other side the same thing will happen, and so the parts of the nucleotide that make it unique will hydrogen bond together, and the like angles of the bond force it to wrap in a double helix, and then the phosphate backbones kind of like curve around each other to form like the iconic structure. There are other shapes of DNA though, depending on your environment.
Does a tree or a bacterium have the same little four, just juggled around differently?
Yeah. Well, a bacteria might have RNA instead of DNA. Most bacteria have single-stranded RNA or single-stranded DNA, not necessarily double-stranded DNA. It depends. But it will be the same 4 or 5 nucleotides. They never change across life.
Well,
This is great. If I ever give this talk again, we'll like tag team. I'll do the first part and you do the second part.
Well, I got to tell you, Dr. Nikolaus, you did good. We appreciate you. Something that didn't get asked, but it does cross my mind here. If we're going to go out and mine asteroids, is there a way we could go out and get some? No, I guess not. I have for you, my friend, a priceless piece of porcelain dug up from an Indian ancient Chumash burial ground. Don't put your tea in it because your check is in there for honorarium. Thank you. Dr. Nikolaus Thursday night. But are you going to be there this week? At Astronomy on Tap?
I will not.
Okay, but the little lady was giving the speech on black holes, sucking everything else. Well, everything else, she's going to be running the show, and you work with her, I think. Sandy Seal, thank you very much. She's the one that gives us our raffle tickets out here in the city. We talk about dangerous asteroids. Thank you for coming, everybody, on behalf of the president.